This video runs through two worksheets on financial mathematics in advanced mathematics. So we have annuities and superannuation, and after that we have loan repayments. So an annuity is a savings plan. You deposit the same amount every year and you earn compound interest. The example given here, if you deposit $1,000 at the beginning of every year and you earn 5% interest compounded annually, then that will amount to over $7,000 at the end. And because we made 6 deposits of $1,000 each, then it's easy to calculate how much actual interest was earned. This is a much more complicated scenario than a compound interest question, where a single payment is made and then interest is earned over time. So the particulars of the conditions are that the same deposit is made at the beginning of every year and the interest compounds annually. Now, different questions can have different conditions. It's important to read them carefully. And it means that there's no one-size-fits-all approach here. Alright, so annuity calculations are much more complicated than compound interest calculations because of the regular deposits. We don't have a formula for calculating the future value of an annuity, but we do have a process demonstrated here today. Superannuation this is for student interest. Superannuation is a process by which workers make regular contributions towards their retirement savings. It differs, real life differs from what we're doing here because of changes in interest rate, changes in payments, etc. Okay, so best way to get started with this is to look at a table. So if we're doing $1,000 every year, then the starting balance plus the $1,000 deposit gives us a starting balance of 0, plus the $1,000 deposit gives us $1,000, and then multiplied by 1.05 to account for interest gives us the $1,050 at the end of the first year. So at the start of the second year we have $1,050. We add the $1,000, we get $2,050. Multiply by 1.05 and we've got this ending balance. And so it continues. So 2,000, I'm just using my calculator here, 2152.5 plus 1,000 equals, and then multiplied by 1.05 equals, I forgot to write this down, so that's 3152.50, and then the with interest applied we have 3310 it's 125, I'll round it. Okay, so take that. I'll actually do the round, I'll use rounded values in my calculator. I know that won't be perfectly accurate, but that's just what I'll do. And alright, so if we add $1,000, and then apply the interest, okay, and on it goes. Alright, so naturally with superannuation or any savings plan, we'd like to know the potential future value decades out, and so working it out in a table like this is not great. The balance after 6 years is given by this beast of an expression, which is not practical, just included for interest. It just shows what we're doing. We've got the original $1,000, and then interest is applied, then we make another deposit, then interest is applied, then we make another deposit, then interest is applied to everything so far, and so on. So it just works its way out, and it just shows that working out the future value of this is quite complicated, and it's quite amazing that we can do it at all. Worth pointing out, not included in this worksheet, but is good to include in teaching. The idea, and first also I would start this at 0, but right, whatever. Okay, so if A1 equals 0, that's the starting balance of year 1. And then A2 is A1 plus 1,000 multiplied by R. I'll just say R is 1.05. And A3 is A2 plus 1,000 times R, and A4 is A3 plus 1,000 times R, and so on. Then this can be calculated actually very quickly on the calculator using the answer key. So I can't show it, but I can talk through it. So I'm going to put 0 equals, and so now the answer memory has 0 in it. And now I'm on to this line here, and I'm going bracket answer plus 1,000 close bracket times 1.05. I hit equals and I get 1,050. Okay, so I've achieved this, and then when I press equals, well, now I've got this, and when I press equals again, now I've got this. So you can actually rattle through the years very quickly by just pressing equals. So you can't use, it still is a complicated, it's a recursive calculation. You can't use a power to shortcut things like you can with compound interest, but by keeping track of how many times you've pressed equals, you can work it out for many years in the future. Okay, so we're going to now look at this a different way using series. Okay, so this method is more complicated, but it allows us to do calculations over longer time periods. We'll consider each year's deposit separately and the interest that it earns separately. The first deposit is $1,000, and it earns interest for, well, we're doing this over, let's say we're doing this over 40 years. Oh no, sorry, we're doing, the scenario is that we're doing this scenario here, right? So it's over 6 years. Right. The first deposit, well, it was $1,000 and it earns interest for 6 years. Now, was it 6 years or was it 5 years? Got to be very careful about these things. Let's maybe count it. So the $1,000 deposit was multiplied by 1.05 here, and here, and here, and here, and here, and here. And we're talking about the balance after 6 years, and we started at 1, so that's this. Okay, so yes, I'm satisfied, and we always need to check. I'm satisfied that this earned money for 6 years, earned interest for 6 years. Over that time, it reaches a total value of, well, that's $1,000 times 1.05 to the power of 6. So that's a compound interest calculation. That's the amount earned by the first deposit. The second deposit is $1,000 and it earned interest for 5 years. So over that time, reached a total value of $1,000 times 1.05 to the power of 5. And we'll call this amount A2, the amount earned by the second deposit. The third deposit, we've got 1,000 times 1.05 to the power of 4. Fourth deposit, like so. The second deposit, like so. And the fifth deposit, and then the sixth deposit. Okay, so that earned money for 1 year, earned interest for 1 year. We can see that here. We had a starting balance at the start of the 6th year. We're ignoring that. We're just looking at the deposit and how it earned interest for 1 year at the end. So the final balance is is this sum. Okay, now I haven't calculated each individual thing here. Not too interested in doing that. But I suppose as a classroom activity, introducing this, that's a good idea. All right, so we can calculate the final balance without using intermediate values as follows. So so we have $1,000, we've got 1.05 to the 6 plus $1,000, 1.05 to the 5 plus, and so on. We can factor out the $1,000 and just reverse the just reverse the powers there, makes it look like a better geometric series, and that is a geometric series. So right, so this is a geometric series with A equals 1.05, R equals 1.05, and N equals 6. Okay, so this is $1,000 times that value, and I'm gonna put this in my calculator and hope for the best. Okay, so I have got 7,142.01, and that is what we have here, right? And what we would have found in the table if I'd kept it going. Okay, so that just demonstrates how these can be calculated over a very long time if necessary. Right, moving on to loan repayments. I'll just say before moving on, I think it's pretty common. So I've set out the conditions here, which I think are realistic conditions. Right, you make your deposit at the beginning of every year, and you earn interest on it, or the beginning of every month, or whatever. There are some times where, and maybe even common times, where questions say ridiculous things like deposits paid at the end of each period, and so the first one doesn't earn any interest. The important thing is, whatever the conditions are, you can set it out in a table, if that helps, and you can set it out in this sort of approach, an algebraic approach. Okay, loan repayments. So loans are repaid using reducible interest. You make a regular monthly repayment. The interest for that month is calculated based on your current balance for that month. So as your balance goes down, the interest goes down, and crucially, more of your repayment is going towards paying off the loan rather than paying interest. So for today's example, we'll consider a loan of $5,000 at an interest rate of 18% per annum, 1.5% per month, and repayments of $130 per month. So for a small number of months, we can work out in a table. So we've got a starting balance of $5,000 plus the 1.5% interest gives us this value, and then take off the repayment, and that's how much is owing at the end of the first month, and of course that carries over to the beginning of the second month. I will say once again, I made this sheet many years ago actually. These days I would start with 0, 1, 2, 3. The idea of 0 being you haven't made any payments yet. All right, so 4,945, just for sake of demonstration. I'll continue a little bit, so 4,945. We're going to do plus, no, I'm not going to do plus, I'm going to do times 1.015. That's accounting for the interest. So I get 5019.18, just rounding there. And then I'm going to take away the 130. And I've got 4889.18. Alright, so that's carried over. Students don't mind doing this sort of thing, not asking too much. Okay, so I've carried that over. I've got the more accurate value in my calculator, I might as well use it. So times 1.015 equals 4962.51, and then subtract the repayment. Etc. So a couple of discussion points here. I guess we can look at, we could put a new column here, the amount paid off. And all we're doing is looking at, so at the end of the first month, we owed 4,945. At the beginning, we owed 5,000. So what's the difference there? I don't need a calculator for that, but I don't want to make a mistake. So, okay, so $55. So we made $130 repayment, but only $55 of it was effective. And you could work out the percent effectiveness as well. I've done these things in class before. And just to demonstrate, 4889.18 minus 4945. That gives me a negative number, but that's okay. $55.82. So, you know, slightly more effective in the second month than the first. And if you use a spreadsheet, you can put these columns into the spreadsheet and then muck around with different regular repayments, and you see that if you make greater repayments, then you're getting a greater increase in effectiveness as you go. So there are several good life lessons that are part of this topic. All right, so just a little bit of, I guess, a first algebraic approach here, just like with the last one, and this is to support using a calculator efficiently. So I've got A1 is 5,000. I'm going to set R equals 1.015. So A2 is A1R minus 130. And A3 is A2R minus 130. And A4 is A3R minus 130, etc. So how do we do this in a calculator? I'll write the steps down. Write 5,000 equals. I'll do that. 5,000 equals. So now 5,000 is in the answer memory. And then these all have the same structure, don't they? The A1, A2, A3 is the answer. So I'll go ants, answer, times, I could put 0.1.015 minus 130 equals, so if I do that, I get answer times 1.015 minus 130, so I get 4945. And then when I press equals again, I'm repeating the calculation but with a new value in the answer memory. And I get 4889.175. Okay, so I've got that. You get as many of these as you like. You can answer the question, how long does it take to pay off? You just keep pressing equals and count how many times you had to press equals. Okay, so that's a very worthwhile thing to do. Okay, how much is still owing after 2 years? So we're looking at 24 months here. So we'll work it out another way, which is the same as this to begin with, but brings a little bit more algebraic sophistication in. All right, so I can't resist writing 0, but okay, A1 equals 5,000 and R equals 1.015. Yes, and it's worth saying what we mean here. And what's more, I'm going to use B for balance because I notice that's commonly what's done in textbooks when we're talking about a loan balance. It doesn't matter what the letter is, of course, but we need to make sure that we're not stuck on using A all the time and getting confused with something else. So BN equals the loan balance at the beginning of month N. Okay, and we seek B24, right? That's false. I just wanted to see if you catch me out. It's B25 we need. If we want to know the balance after 2 years, that's the balance at the end of the 24th month. But this is set to the beginning of a month, so the end of the 24th month is the same as the beginning of the 25th month. All right, on we go. B2 equals B1R minus, now I'll set M equals 130 for the regular monthly repayment. I don't want to write 130 lots of times, so I'm going to write M. So B2 equals B1R minus M. Don't think there's anything I'm going to do with that. So B3 equals B2R minus M. But that is, so B2 can be replaced with B1R minus M. And then I've got R minus M. So just emphasizing what's taken place there. And that is B1 R squared minus M R minus M. Okay, important to do one more of these. B4 equals B3R minus M. Same sort of substitution is going to take place. So the B3R minus M, right? But what is B3? Well, we've got it here. So that's B1 R squared minus MR minus M. Right, so if we expand all this out, we get B1 R cubed minus MR squared minus MR minus M, and it's about time that we did this. And we can see that that pattern will continue. This is Incidentally, why I start at 0, because just for that agreement. And so in this case, BN is the loan balance after n months, and we would seek B24, the balance after 24 months. Anyway, we have to, like I prefer what's in red, but I'm going to continue with what's in blue. If other people, like an exam committee, set up the question for us, we don't have a choice anyway. Okay, so B4 is this, so continuing or extrapolating or something, B25 equals B1 R to the 24 minus M 1 plus R squared plus dot 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 plus R to the 23. Right, there was a pattern here of 4, 3, 2. Well, it's 25, 24, 23. Okay, and this, well, B1 was 5,000. Right, this is 1.015 to the 24. M is 130. And going to do a little aside here. So the SN equals A R to the N minus 1 over R minus 1. Our A equals 1, R equals 1.015, and N is 24. Okay, there are 24 terms there because that goes from R to the 0 up to R to the 23. That's 24 terms. Right, so I'm just going to calculate this. So that goes in there. Continue with my calculation, and I'll say 5,000 times 1.015 to the power of 24 minus 130 times my answer. So that is 3425.16. Okay. Now, just a nice point to be made here. This value here has a meaning, and I always insist on students calculating it and writing it down because it has a meaning. $130 is how much we're paying per month, and it's been 24 months. So of our own money, 130 times $24 has been paid. But this means that we're getting 28.6 months of value. All right, so that extra 4.6 months is the benefit of interest. So there's meaning to this number, and it's nice to understand. Looking ahead to the next question. Right, so then The next question is how long will it take to pay off the loan? Well, let's just do it. Okay, so this is okay. Sorry, it's a different question. It's how much will the monthly repayment be if we're going to do 36 payments? So let me answer this question here. Different colour. Clear some room. Okay, so basically BN, following our pattern, is B1 R to the n minus 1 minus M 1 plus R squared plus dot 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 plus, and it goes up to R to the n minus 2. That's what's happened in this scenario. So how many months to pay off? That's the obvious question. Well, that means we are solving Bn equals 0 for n. Now, if you solve A equals B minus C, and you're putting A equals 0, then you're getting B equals C. Here's your A, here's your B, here's your C. All right? So what we get here is that B1 R to the n minus 1 equals M 1 plus R squared plus dot 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 plus R to the n minus 2. Okay, and once again, these have been neater if I started counting at 0, but that's fine. This is very nice. There's a very nice insight here. On the left-hand side is compound interest. Okay, our B1 was $5,000. That was the loan amount. And the right-hand side is the kind of calculation that goes with a savings plan. So basically what's saying is that on the left-hand side, if we put the $5,000, 1.015 to the power of n minus 1. So if we didn't make any payments, then our loan balance would just go up and up and up. Right? But on the other hand, if we let's say we didn't make any payments, the loan balance is going up and up. But over here, we're doing a savings plan in a different account and earning money, and eventually the amount that we've saved equals the amount that the loan has grown to, and at that point we withdraw all of the money we've saved and pay off the loan. It's a very curious way of looking at what's actually going on here. So I won't complete that calculation. That's just another series calculation and then some more algebra. And all right, last question. So the loan is to be fully repaid in 3 years. How much is the monthly repayment? So our B1 is well, I can quote this. Okay, so that's that is the the balance at the beginning of month N from memory. Yes. Okay, loan is to be fully repaid, so that's BN equals 0. Well, in 3 years, so that's N equals, well, we've got to do 37 because it's after 36 months, so at the beginning of the 37th month. All right, so we're going to solve B37 equals 0. How much is the monthly repayment? So for M, given, well, there'll be 36 payments and the interest rate. So given R equals 1.015, that's all we need. Okay, so all right, so if Bn is 0, then we've got B1R and N minus 1 is 36 equals M outside 1 plus okay, there are N minus 1 terms in this this series. Okay, so I can't replace the series with a number because we've still got an N in it. Oh no, silly me, sorry. N was 37, so this is okay, so I can replace this. Just got to work it out. Okay, so back to the blue. So the B1 is 5,000. Then we've got 1.015 to the 36 equals M times 45.59208 ... Keep that in answer. And we're trying to find M, and everything's calculatable now. So I'm not even going to write out another line, I'm just going to calculate it. So 5,000 okay, so that's months. All right, so the balance at the beginning of, all right, so B187 will be greater than 0. B188 will be less than 0. So at the beginning of month 187, we won't have paid it off, right? At the beginning of month 188, the loan will be paid in full. Whoops. All right, well, I can't edit the video, but that was a terrible mistake. So forget all of this. We know how long the loan is taking to pay. This is not months, this is dollars. Okay, so repay $187.44 near a cent per month to pay the loan in 3 years. There we go. All right, hope that was helpful.